Good afternoon, everybody. Welcome to today's lecture. And as you can see from slide 1, we're going to be talking about ADC architectures today. We're going to consider four main types. We're going to consider the flash, the half-flash, the pipeline ADC, and the successive approximation ADC, spending most of our time on the flash, the half-flash, and the pipeline, because we've already spent a little bit of time on the SAR ADC in the context of the mini project. Now, we will also briefly mention the integrating ADC, the algorithmic ADC, and the oversampling ADC. These are important in their own right. The integrating ADC is important as it's a very famous architecture. There was a very famous integrated circuit called the ICL 7106. They still make them, not in the volumes they used to make them in. They have sold literally hundreds of millions of these chips. They were used in all sorts of sensor systems, weighing scales, digital multimeters, and so on over many, many decades. Nowadays, that task is primarily carried out by either microcontrollers with built-in data converters or the architecture shown at the bottom of the list here called the oversampling ADC or the sigma delta ADC. So let's go and look at the first technique, the flash ADC, so called because flash signifying great speed. It's the fastest possible way to do ADC conversion. The ADC conversion is achieved in a single clock cycle. We'll talk about that in a moment. Frequently called also the parallel ADC, simply because the conversion is carried out literally in one parallel single clock operation. If we look here at the left hand side of this schematic, you'll see 4 resistors, and the reason for the 4 resistors here is because this is only a 2-bit ADC for example purposes. So we need just 2 to the power of 2 or 4 resistors to divide the reference, which is connected between VREF plus and VREF minus, to connect it up into 4 different values. So if we assume for the moment that VREF minus is connected to ground and VREF plus is connected to 4 volts, tap 1 we should see 1 volt, tap 2 we should see 2 volts, tap 3 we should see 3 volts, and then of course the reference is at 4 volts. These tap points are connected into the minus inputs of the comparator C1, 2, and 3. And you should be able to see at this point that Vin, which is connected into the positive input of every single comparator here, that as Vin exceeds 1 volt, the first tap point, comparator C1 will trip, giving us a logic 1 at the output here. As Vin exceeds 2 volts, which is the value sitting on tap point 2, comparator C2 should trip, giving us a logic 1 at the output of C2. And then further on, if Vin exceeds 3 volts, comparator C3 should now trip, giving us a logic 1 at the output of C3. So if you can imagine for a moment this were a 4-bit flash ADC, and remember we're going to have 2 to the power of n minus 1 comparators in this column of, or bank of comparators. So for a 4-bit ADC we would have 2 to the power of n, 2 to the power of 4, 16 minus 1, we would have a bank or a column of 15 comparators. So if you can imagine Vin rising and falling in value between 0 and Vin full scale, what you should see at the output of this column of comparators is a column of 1s rising and falling as Vn increases and decreases. And that's the reason why the code coming from this column or bank of comparators is referred to as a thermometer code. Now the next thing that must happen is we need to see this thermometer code being converted into a usable binary code at the output, and for that, in this 2-bit case, we need a 3 to 2 line encoder logic circuit, and we'll talk more about this later on in the lecture. For the moment, let's switch over to our drawing tool, and I'll select the paintbrush here, which won't necessarily be pretty, but it'll do the job, and make a truth table for those comparators. So there's comparator 3, comparator 2, comparator 1, and we'll reserve a couple of columns here for D0 and D1. So there's C3, C2, C1, D0 and D1. So we're going to have a number of different states here. We'll have zero, zero, zero. We'll have 0, 0, 1. That's when comparator C1 has tripped. We'll have 0, 1, 1. And then finally we'll have 1, 1, 1, but all three comparators will trip. And so our decoder will need to give us the code, the binary code 0, 0, when none of the comparators have tripped. We would like to see 0, 1 appearing when comparator C1 is tripped. We would like to see 1, 0 when the first two comparators are tripped. And then we would like to see the code 1, 1 when all three comparators have tripped. In other words, when V in has exceeded 3 volts.